Hello everybody, thank you for watching. My name is Anton van Oosten. I will introduce you to the wave theory of classical electromagnetism. In the following, I will motivate and validate the wave theory of electromagnetism. In the process, I will abandon the Gates principle of electromagnetism. So let me first explain what is the Gates principle. It is a complex and broad subject. Gate invariance involves very complex mathematical concepts. It is applied throughout field theory and therefore may take on different forms. In the context of electromagnetism, it means that the potential can be changed by a local transformation without physical consequences. The Gates principle is considered the most important principle of theoretical physics. It is the guiding principle for the coupling of particles and fields, and as such it forms the basis of the Standard Model. The Gates principle also has a touch of magic to it, as it holds many theoretical physicists under its spell. The Gates principle has its roots in classical electromagnetism. Let's take a close look at the Maxwell equations. Here is the traditional representation in terms of the electric field E and the magnetic field B. There are two sourced and two source-free equations. E and B are not vectors, however. They are components of the antisymmetric field tensor F, and this allows us to write the equations in an explicitly Lorentz covariant form. I use the metric with negative g00 and units such that light speed c equals 1. Using F, the two sourced equations reduce to a single one that equates the divergency of F to the charge current source. The two source-free equations reduce to a single mathematical constraint on F. This constraint guarantees the existence of the four-potential A, of which the field tensor is the rotation. And with that, I now have a single second-order inhomogeneous differential equation in terms of the four-potential A. Electromagnetic gauge invariance means that the field tensor F is invariant under a rotation-free addition to the potential A, so that A is not physically determined. The gradient of any differentiable scalar field is rotation-free and can therefore be added to A without physical consequence. The arbitrariness of the scalar field, of which the gradient we can add to the potential A, means that anything goes. This image is a stationary 2D example of an arbitrary scalar, but a 3D scan of your favorite pet walking around would also do. The electromagnetic potential is of central importance in field theory. It is therefore curious that it would be of limited physical meaning. Here I propose the wave theory of electromagnetism, in which the potential has full physical meaning. The discussion will be limited to classical theory. Consider the second-order inhomogeneous differential equation that I just derived. The first term on the left-hand side involves the D'Alembertian operator known from wave equations. It preserves the vector character of A. The second term couples the coordinate system to the potential A and compromises its vector character. It vanishes if the Lorentz gauge is chosen. For this particular choice of gauge, the physically appealing wave equation holds. Here I propose a more radical solution. Drop the second term altogether so that the wave equation always holds. This leads to what I call the wave theory of electromagnetism. By this radical step, I give up gauge invariance altogether. Can I get away with this? In the rest of the video, I hope to convince you that I can. Wave and gauge theory lead to the same field tensor. Also, wave theory gives a more intuitive account of quantities like energy, energy transport and spin. Yet, when gravity is considered, wave and gauge theory are experimentally different. The solution of the wave equation was already given in 1867 by Ludwig Lorentz in the form of a Green's function. For the gauge theory, this solution formally does not hold. Gauge invariance means that the Maxwell equation cannot be inverted. In practice it works, though, and we all use this solution. However, the wave equation can be inverted. It defines a one-on-one relation between potential and source. Therefore, charge current conservation here implies the Lorentz condition. It is a law following from charge current conservation, not an arbitrary choice of gauge. What about the solutions to the Maxwell equation that do not obey the Lorentz condition? These solve the wave equation, so have the correct electrodynamics, but they describe situations where current is not conserved. Mathematically, I can still change A by a solution of the homogeneous wave equation, which has vanishing source in all of Minkowski space. Such solutions are eliminated by a boundary condition resulting from causality. Here is a sketch of the light cone of a source located at a point in Minkowski space. Outside the light cone lies the region of Minkowski space that has not affected the source and never will be affected by it. Causality therefore implies that a source at the origin has zero potential outside the light cone. Now, a solution of the homogeneous wave equation that is zero outside the light cone must be zero also inside the light cone, since it has no source anywhere. The conclusion is that the wave theory has a fully determined potential. It leads to the same electrodynamics and yet is experimentally different from Maxwell theory. I will now use the action principle and the Noether theorem to motivate rigorous expressions for the energy, momentum, and angular momentum of wave theory and gauge theory. These will be applied to elementary physical situations to compare the theories. The field equations are derived from a suitably chosen Lagrangian using the action principle. The Lagrangian is a functional of the potential derivatives alone, because the electromagnetic field is massless. For the wave theory, the Lagrangian is the sum of squares of the potential derivatives. The action principle leads to the Euler-Lagrange equation, which gives the free wave equation. The conservation laws are found from the global symmetries of the Lagrangians, using the Noether theorem. Energy-momentum conservation follows from invariance of the Lagrangian to the choice of space-time origin. The resulting energy-momentum tensor is symmetric as required by gravitation. Power force is the rate of transfer of energy-momentum to the field. It is equal to the negative of the divergency of the energy-momentum. It vanishes in the absence of charge current. Orbital momentum conservation follows from invariance of the Lagrangian to Lorentz transformations of the space-time coordinates. The Noether expression is the generalization of the cross product of lever arm and linear momentum. Spin angular momentum conservation follows from invariance under Lorentz transformations of the potential. Spin is generically non-gauge invariant. The spin tensor of wave theory is directly related to the circular polarization of the field. Orbital and spin angular momentum are separately conserved due to the high symmetry of the wave Lagrangian. For the gauge theory, the field Lagrangian is the square of the force tensor. It leads to the source-free Maxwell equations. For the gauge theory, the Noether theorem gives an energy-momentum tensor that is not gauge invariant. It also is not symmetrical as required by gravitation. Again, we find an orbital and a spin contribution to the angular momentum. The spin contribution is not gauge invariant, and only the sum of orbital and spin angular momentum is conserved. The standard procedure to repair the asymmetry of the energy-momentum tensor and the lack of gauge invariance is energy-momentum symmetrization. Using the generic expression, a correction term is derived from the gauge invariant Lagrangian. Adding this correction to the energy momentum symmetrizes the tensor and makes it gauge invariant. A further effect is that it removes the spin angular momentum. All electromagnetic angular momentum is now orbital angular momentum. Next, I include the source by adding a Lagrangian that represents matter plus interaction. In this way, I obtain the inhomogeneous wave equation and the Maxwell equation. The source term in the right-hand side stems from the mass plus interaction Lagrangian. The energy momentum now consists of a field term and a mass plus interaction term. This is also the case for the gauge theory before symmetrization. The power force is equal to only part of the Lorentz force. The reason is that the interaction energy momentum is not included in the field. This is true for the wave theory and for the gauge theory before symmetrization. The expressions of orbital and spin momentum remain formally the same. The orbital momentum now contains contributions from the field and from the matter plus interaction. For convenience, I have assumed that the source has no spin. Let's symmetrize the gauge theory again. The Bell-Infante-Rosenfeld correction now contains an additional interaction term. Upon symmetrization, the field energy momentum is again symmetric and gauge invariant. Additionally, there is the matter plus interaction term minus j mu a nu. This must equal the matter kinetic energy momentum, Tm, without interaction contribution. Indeed, the symmetrized field energy momentum alone leads to the Lorentz force by the Maxwell equation. Thus I can replace Tmi by Tm plus a mu j nu in the wave theory energy momentum. Let's take a closer look at the field theoretical results. First, consider the energy and momentum distributions. For the gauge theory, the energy is the familiar E square plus B square. The energy transport distribution is the Poynting vector. It is identical to the momentum distribution. Even for static fields, the Poynting vector can be non-zero. There is no source contribution, hence no potential energy. There is no Q times V. For the wave theory, the field energy is a summation over squares of the potential derivatives. An electrostatic field has negative energy. The field energy transport is the sum of the product of the time derivatives and the space derivatives of the forward potential. For the field, it is equal to the momentum distribution. Unlike the Poynting vector, it vanishes for static fields. The source contribution is the familiar scalar potential energy of the source. The source contributes potential energy transport, and potential momentum. For the gauge theory, the force is the Lorentz force. It is entirely determined by the field. The wave theory splits this in two. The first part is interpreted as the time derivative of the potential momentum of the source. It is moved to the left-hand side of the force equation. The remaining force equals the time derivative of kinetic plus potential momentum of the source. The source should have potential momentum as it also has potential energy. In the gauge theory, there is no spin, only orbital momentum. In the wave theory, the free field has separately conserved orbital and spin angular momentum. I will now validate the wave theory by applying it to a number of elementary examples. Some of these are taken from the Feynman Lectures Part 2, Chapter 27. Consider a simple example of electrostatic energy, namely two stationary positive charges. The drawing shows the total electrostatic field. In the gauge theory, the energy distribution comes from the field and is half E square. In the wave theory, the source contributes the potential energy and the field minus half E square. Disregarding the self-energies, the energy distribution is E1 times E2 for the gauge theory. For the wave theory, it is Q1 V2 plus Q2 V1 minus E1 times E2. The source term double counts the energy, but this is corrected by including the field term. It is tempting to say that the electric field exists because it lowers the energy. The two theories differ only by an integration by parts, and their volume integral of the energy is the same. The energy distribution, however, is very different between the theories. Hence, the gravitational field is very different, although it is minute and experimentally beyond reach. Thus, the two theories are in principle physically different. Next, consider a well-known paradox involving the Lorentz force. Two identical charges move orthogonally in a common plane at the same speed. Does the Lorentz force between them obey Newton's third law? The electric forces are equal and opposite, but the magnetic forces are mutually orthogonal. The total particle momentum is not conserved. Newton's third law does not seem to hold. This is a paradox, as momentum should always be conserved. Apparently, gauge theory only conserves the total momentum of particles plus field. Is there some hidden momentum in the field? The wave theory solves the paradox. It separately conserves field and particle momentum. In wave theory, particle momentum consists of kinetic and potential momentum, just like particle energy consists of kinetic and potential energy. Let's take a look at the proof. This is the rate of change of the momentum of particle 1 in wave theory. Here's that of particle 2. These are collinear and opposite forces as required by the third law. In wave theory, there is no paradox. Total particle momentum is conserved. In gauge theory, the particle potential momentum resides in the field in partially integrated form. This momentum is transferred to the particles so that it appears as if their total momentum is not conserved. The third law holds. Newton and Maxwell agree. The origin of the paradox is that gauge theory incorporates matter potential energy and momentum into the field. This is caused by Belinfante-Rosenfeld symmetrization. As the next example, consider a resistive wire carrying a constant current. Ohm's law tells us that heat is generated along the wire. The seemingly trivial question is, where does the energy come from? This was discussed by Poynting in 1883, Heaviside in 1892, and Feynman in 1963. The intuition of the Drude and the Drude-Sommerfeld models is that the energy is delivered by the electrons. They are accelerated by the electric field from a voltage source, and then their energy is thermalized by scattering. The result is a small drift velocity and energy transfer to the metal. Let's see what each theory says. Here are the general formulas. For the gauge theory, the energy transport is given by the Poynting vector. Inside the wire, the electric field is parallel to the current. The electric field component parallel to the wire is continuous across the boundary, so just outside the wire there is a Poynting vector component perpendicular to its surface. Thus the energy required for the ohmic dissipation comes from outside the wire. As Poynting wrote in 1883, it seems that none of the energy of a current travels along the wire, but that it comes in from the non-conducting medium surrounding the wire. For the wave theory, the energy transport reduces to simply current times potential. You can readily transform this into your favorite expression using Ohm's law. The potentials are constant in time, so the field does not transport energy. Thus, all transport is done through the wire by the electrons. Both formulas deliver the same energy. Summarizing, in gauge theory, the heat comes from space. Wave theory is much less exciting. The energy simply comes through the wire. Here's another example on energy transport with static potentials. Feynman says it well.
Finally, in order to continue to convince you that this theory is obviously nuts,
in this case, a charge is placed near a magnetic dipole. This was already discussed in 1904 by J.J. Thomson, who discovered the electron. The Poynting vector tells us that there is an energy circulating in space. Wave theory says that there is only an energy flow inside the magnet associated with the source of the dipole field, which I take to be a current loop. Again, gauge theory challenges intuition, while wave theory gives an unsurprising but intuitive answer. This example from Feynman's lectures
there's angular momentum in this space,
is known as the rotating disk paradox. An insulating disk is free to rotate. Charged metal spheres are attached to its surface. Also attached is a current-carrying coil of wire fed by a battery. Initially, the disk is at rest. Then the battery is disconnected. As a result, the disk will start turning. The question then is, where does the angular momentum come from? Gauge theory states that there is angular momentum equal to r cross the Poynting vector stored in space, and that it is this field angular momentum that is transferred to the disk. Wave theory says that as the potentials are static, the field contains no angular momentum. Instead, there is angular momentum in the magnet itself. When the battery is disconnected, this is transferred to the disk, causing it to rotate. Again, wave theory explains this experiment in an intuitive, hardly surprising way. Now I will discuss electromagnetic spin. This is the intrinsic angular momentum associated with the vector nature of electromagnetism. There can be no gauge invariant expression for spin, so in gauge theory there is no spin. Spin is absorbed into orbital angular momentum as a result of symmetrization. In wave theory, on the other hand, there is both orbital and spin angular momentum. These are separately conserved in the absence of sources. Now consider a monochromatic plane wave that is circularly polarized. In gauge theory, there is no angular momentum density along the propagation direction, because orbital angular momentum is perpendicular to the Poynting vector. In wave theory, there is uniform spin density, and this is equal to the energy density divided by the frequency. This is also what is expected if light describes photons carrying spin 1. Both theories should predict the same total angular momentum, so this is a bit of a paradox. The solution is that in gauge theory the missing angular momentum shows up far away, where the wave is no longer plane. Now what happens if the angular momentum of such a wave is measured with the torsion balance? This was done by Richard Beth in 1935. A circular light absorber is suspended from a torsion meter, and circularly polarized light shines on the absorber. A torque is expected and was indeed measured. Gauge theory, however, seems to predict a zero result. Wave theory predicts a torque equal to the power absorbed divided by the frequency, as was measured. How can this paradox be resolved? For the answer, we should look behind the absorber. Here the wave is no longer plane. In gauge theory, the Poynting vector there gives a sharp distribution of momentum that encircles the wire on the edge of the shadow region. This gives a sharp distribution of orbital angular momentum, making up for the torque. In gauge theory, it is less than straightforward to predict the correct experimental result. Also, it is difficult to see how gauge theory aligns with the understanding of this light beam as a uniform flux of spin-polarized photons. The conclusion is that wave theory gives a natural account of spin, while gauge theory is almost misleading. I conclude that wave theory is a valid theory of classical electromagnetism. It requires fewer assumptions than gauge theory, as it does not require the gauge principle. Its description is closer to our intuition. In static cases, energy transport and angular momentum reside in matter. These do not reside in fields in otherwise empty space. All this is in agreement with the venerable methodological principle of Occam's razor, which has that no more things should be presumed to exist than are absolutely necessary. An important feature of wave theory is that it supports the concept of electromagnetic spin. Thus, wave theory is a natural starting point for a theory of spin-carrying photons. A corollary to Occam's razor could be that things that are observed should be clearly described by the theory. Last but not least, wave theory is experimentally different from gauge theory due to its implications for gravitation. This is not diminished by the fact that such a validation is beyond foreseeable experimental means. And by this, we've come to the end of my presentation. I thank you all for your attention. Please send any comments to anton.van.oosten@gmail.com with header wave theory. Thank you.